So hello YouTube. So this is a video on SolidWorks simulation where we are going to perform dynamic simulation on this sheet metal bending geometry. Okay, so I will just show you how this sheet metal bending is going to be performed. So this is the animation. I have created a video on how to animate. Okay, so now what is dynamic analysis? So dynamic analysis is a contrary of the static analysis. It is also called as non-linear analysis, wherein the load conditions vary in magnitude and direction over the time. Okay, so this is a complex geometry. Here we are going to perform the dynamic analysis. Okay, so for simulation you will have to go in SolidWorks add-ins, check onto the SolidWorks simulation, and then the simulation tab will appear over here. Click onto the simulation tab, go on new study. Here choose non-linear and choose use 2D simplification to transform all this 3D into a single non-thickness 2D geometry, because this geometry is symmetric over a plane. So when a geometry is symmetric over any of the plane, then we are going to use 2D simplification. Now as this geometry is symmetric over the front plane, so we are going to choose front plane. And now I have forgot what is the thickness of this geometry. So what we'll do is we'll go to the evaluate, we'll go to measure, and we'll measure this length. So this length is 35 mm. So I will input the value over here. 35 mm is the input value. Check on to right. So the first step of the simulation, so see, it is converted into a non-thickness 2D geometry. And now as it is symmetric over the front plane, so now we'll perform our simulation on this and then we'll convert it into 3D. So this will reduce our simulation time and the accuracy will be increased, and it will be same, okay, for over the geometry. But this is done only when the geometry is symmetric. The first step of the simulation is the material application. So we'll right click, we'll go on apply material, and we'll click on copper. Now I am choosing copper material for the sheet because the sheet should be elastic. Okay, it should have the property of elasticity because we are going to bend it. Okay, in case of the die and the punch, the I'm going to select plain carbon steel. Okay, now the next part is the connection. So this connection, I will just click on right click, local interaction. So here we have to give the contact between the punch and the sheet. Okay, this is also very important step. So I will choose this edge of the sheet and this edges of the punch. Now here we are selecting edges because this is a 2D geometry. We have converted the 3D into a 2D geometry. But this is actually the faces that we are selecting. Okay. Now as we have gained the contact, now the next step is the addition of the fixture. So what are the fixed geometry? So this edge of the die are going to be fixed. So click on all the edges and click on fixed geometry. Okay. Now to hide these arrows, just right click on the arrows and click on hide. Now the next fixed geometry we are going to give to the sheet. Okay. Now the so the sheet is between the dies, so it is going to be fixed over here. So carefully select the edges of the sheet and click on fixed geometry. Okay, again to hide, right click and click on hide. Now the most important part of the video is that we are going to give motion to the punch into the negative z direction 70 mm. So what we are going to do, we are going to right click and we are going to click fixed geometry, going to click on advanced, going to select the edge. So we are going to select the topmost edge, and here we are going to select this. So this was mm. Yes, so here we are going to select into the z direction. So now you can see this direction is going up, the arrow direction is up. So click on reverse direction and here click on 70 mm, and it should not move. I will choose front plane. Okay, so it should not move uh, into the y direction. So we'll have to also check onto the y direction and specify 0 over here. So now right click. Okay, and you can also hide this. So now all the conditions have been given. We have given contact between the punch and the sheet, and we have also given the motion that the sheet is going to go in the downward direction 70 mm. So now the second last step is just to apply the mesh. So you can create a finer mesh, but that will result into the uh, more time for the results. Okay, but it will also provide accurate results. So I'm going to keep it in middle only and click on create mesh. So see, this is the mesh quality. You can reduce the element size if you want a fine result. And now the last option, the last step is to just run the study. Okay, here click on OK, and here click on no, and see the study is running. Okay, so the time of the study will depend on your system features. Okay, and the performance of your system. So see, the study has been okay. So it has plotted the stress, displacement, and strain. Now this is for the 2D. Now if you want to calculate this for the 3D, what we'll do is we'll just convert this into show as 3D plot. Okay, so see, it is showing that the maximum stress will be generated at this point. Now the maximum stress it is not showing in the floating number. So to convert this into floating number, click on chart option and specify here floating. Okay, so see, now it is showing it into the floating number. Now to animate the entire assembly, what we'll do is just right click. I will choose displacement. Again click here, show as 3D plot, and then I will just right click on animation. Okay, now this is only half animation. If I also want the die to go up and again come down, I will just click over this option and I will do a recalculate. So see, this is the animation, right? You can reduce the speed of the animation if you want. So see, this is the animation. Okay, you can also save it as a AVI file on your desktop. Okay, so now what the problem is that as we have taken the material of the sheet inside as copper. Okay, now if we right click onto the copper, if we go on details, if you go on to the details, here they are showing that the maximum strength is going to be of a 9-digit number, but here if we calculate that maximum stress generated is of a 13-digit number. So in a real life situation, what would happen is that a hell lot of stresses will be generated into the sheet and the sheet may even break. So what we'll do is we'll just change the material of the sheet to a more elastic material. Okay, so I will right click, apply material, and I will change it to a rubber. Now nobody is going to use rubber as a sheet material, but this is just to explain you that how this number will change if we change the material. Okay, and so SolidWorks is good at regeneration, so we'll not have to reapply all the another conditions. We'll just have to click on run study and it will calculate the results. Okay. So again click on OK, click on no, and see it is calculating the results. Okay, so now the stress analysis have been performed. Now if you see the maximum stress in this condition also it will be generated at the same point, and but the value is going to be of 1 2 3 4 5 6 7-digit number. And now if you right click onto the sheet material, that is rubber, if you go on details, here the maximum strength of the rubber, the yield strength and the tensile strength is a 8-digit number. Okay, so this is the 8-digit number and the maximum generated is of a 7-digit number. So this is a safe. So now I will show how to add the factor of safety plot. Okay, so just right click on results and here click on define factor of safety. So here the factor of safety is found to be 7. So that is way enough. The minimum that we need is 1 or 1.5. Okay, so here again I will convert it into a 3D plot. So this is it. Now I also perform this study by taking the sheet metal to be of alloy steel. Okay, because alloy steel is also used for sheet. And here when I defined the factor of safety plot, the FOS was found to be 0.001. So this is not at all a safe condition. But because we have defined here rubber as the sheet material, the factor of safety plot is found to be way more safe. Okay, so in this way you can play on with the materials. You can choose different materials and it will, based on the data inputted of this material, it will give you the proper results. Okay, so this is all about the dynamic analysis. I hope you would have learned something out of this video and you will be able to perform the dynamic analysis. So thanks for watching, whoever watched till end. Thanks a lot.